So we are going to look at critical percolation on Z2. So P will be equal to 1/2. And maybe I will just, okay, I will try to write P 1/2, but maybe I will just write P the whole time. P is always equal to 1/2 for this, and graph is Z2. Okay, and also instead of giving names to events, I will just make lots of drawing. Okay, so, but it's still rigorous math, you know. And our starting point will be the following recall, is that, well, if you look at the probability that in a box whose width is n and whose length in n plus 1, the probability of having an open path linking the left to the right, okay, we have seen that this is equal to 1/2. Okay, if you remember, the argument was that if there is no such path, then there is a dual path which is crossing in the opposite direction. And if you look closely at well, the graph on which the dual path is living, well, it's exactly isometric to the graph you're considering here. And yeah, so part of what I'm going to say today is based on what I found in a paper by Bolobash and Riordan. Okay, so the argument is much older, but they have a nice presentation of the argument. The title of the paper is A Short Proof of Harris-Kiesten theorem. And the reason why I'm mentioning it now is that in this paper, if you look at lemma 3, you have the proof, well, not of this, but of the fact that, you know, this geometric fact that if you don't have an open path like this, you have a dual path that crosses in the other direction. Okay, it's kind of intuitively true, but they give a proof of this, which is kind of understandable. So, okay, so in fact, okay, our starting point will not be exactly this. It will be the fact that, okay, if you take an n by n square, then the probability of crossing, as a consequence, this is larger than 1/2. Okay? Well, simply because if you have a crossing of this rectangle, okay, you have a crossing of this square. Okay, so this event is somehow included in that one. Okay, and here, this is true for any square, okay, because my percolation environment is a translation invariant. So I'm not saying where the origin is, I'm just giving you the size of the square, and of course, well, the direction of the squares, they have to be parallel to the axis of Z2. Okay, so what's the goal of today? We want to find a lower bound on the probability of crossing a rectangle in the largest direction. Okay, so what I mean by a lower bound, I want to show that this is larger than some constant that does not depend on n. Okay, and in fact, what we are going to prove is that this is larger than 1 over 128. Okay, so So before going through this, maybe we should go through some consequences of this to kind of motivate you and to show you that this is interesting. And also, I mean, you will see while we do the proof that this is not something easy, okay? It's kind of, well, it would be very strange that you cannot bound this by a constant, okay? Because if you can, I mean, it's not much more difficult than it doesn't seem much more difficult than to cross a square. But, well, you see the bound you get is much worse. So there must be something going on there. Okay. So, so let me give you a few corollaries. Of star. So my first corollary will be that the probability of crossing a rectangle 2n by 6n, well, this is larger than 2 to the minus 31. Okay, I'm just writing the constants for the sake of writing them, but just to say that maybe you're not, if you're doing this, you're not doing this for having sharp bounds, okay? So this is corollary 1. What's corollary 2? Well, okay, let me now look at some kind of square donut. Well, this is 6n, this is 2n, okay, and okay, this is 2n, this is 2n, okay. And what I'm claiming is that the probability to have an open path that encloses the origin, okay, in the donut is larger than 2 to the minus 124. Okay. What I mean is that it's bounded by something positive which does not depend on n. And the third thing is that if you look at the probability that 0 is connected to the boundary of the box of size n, then this decays like n to the minus alpha with alpha equal to minus log 1 minus 2 to the minus 124 divided by log 3. Okay, so just something positive and very small. Okay, so maybe out of these three things, maybe 3 is the most interesting thing, but the idea is that we will first prove 1, then 2 using 1, and then 3 using 2. But just a comment on 3. So if you remember, we have already proved, okay, that this is larger than 1 over 2 square root of n. Okay, and this is smaller than 3 n to the minus alpha. So with these two bounds, okay, the idea is that you kind of prove that this thing is decaying like a power. Okay, and this is somehow a signature of critical behavior. Okay, below criticality, it decays exponentially. At criticality, it decays like a power. And in the supercritical regime, this decays to a constant, which is positive. Okay, so 3 different behavior. And actually, one could show that the weight converged to the constant is also exponential in the supercritical case. Okay, and one might wonder if it would be possible to prove something like this. So, should it be true that this decays like really like a power? And can we find the exponent psi? So, if this is true, then clearly psi has to be somewhere between alpha and 1/2. Okay? And actually, it's proved for side percolation on the triangular lattice that alpha is, well, sorry, psi. Okay, this exponent here, it's actually, well, it exists, and it's equal to 5/48. Okay, maybe I will come back to this at the end of the class, how people figured out these things. Okay, and this is related to conformal invariance and complex analysis. Okay, and on the square lattice, it's believed to be actually also true with this exponent. Actually, for any planar lattice, even if you don't know what PC is, people believe that the critical behavior should be the same. So that at PC, you should have this, and that the psi should be the same for every lattice. It's just that for the moment, people can only prove it for one specific lattice, which is the triangular lattice when people consider side percolation. So you're opening and closing the sides instead of opening or closing edges. Okay. So, any questions so far before I try to prove the corollaries? Okay. So, maybe I should. I forgot this. Okay, so so all of this is basically a consequence of, okay, 1 and 2, they are consequences of FKG. So, I mean, all the events we are considering today are increasing events. Okay, when you're looking at connection events, they are increasing. If you open edges, you're more connected. Okay, let's try to figure out how to get this using FKG. So, okay, so let's try to look at a rectangle which is 2n by 4n. Okay, so now what I can do is look at this rectangle and this rectangle. Okay, and in the middle I have a, well, it doesn't look like a square, but it's a square. Okay, so now what I have is that if I'm crossing this first rectangle, okay, so, and then I'm crossing this second rectangle, and then I'm crossing the square in the vertical direction, then I have a crossing from left to right in the big rectangle. Okay? So from FKG, what I have is that, well, the probability of this crossing, so for n to n, well, it's larger than the probability of this, which is an intersection. Okay, and by FKG, it is larger than the probability of 3n 2n square times the probability of 2n. Okay, this is larger than 1 over 128. This is larger than 1/2. So what we get is that the probability of having this crossing is larger than 2 to the minus 15, I guess. Okay, this is 2 to the minus 7. 2 times 7 is 14, plus 1, 15. Okay, and then I can repeat this argument. So if I want a box of length 6n, well, what I can do is, I'm sliding my rectangle by n each time. So I can take either 4 rectangles which are 2n by 3n, or maybe what I can do is just take 2 rectangles that are 2n by 4n. And actually, you can check that it gives you exactly the same bound. So in the same manner, I have that this, it is larger, okay, by inclusion. Okay, so this is by inclusion, then which is larger by FKG on this. Square. Okay, this is square because I have 2 rectangles in which this occurs. Okay, so I have the probability of this event square. Okay, because I have 2 different events, but they have the same probability. Times the probability that I'm crossing the square vertically. And this is larger than 2 to the minus 31, because 31 is 2 times 15 plus 1. Okay, so do you all agree so far with the... Okay, so now has anyone an idea about this? But knowing that 124 is 4 times 31. So how do you construct such an event using crossing of rectangles? Yes? No?
You have a cross. If you divide it into 4 rectangles, then you have a cross like this, like this, like this, like this.
Yes, perfect. So this event it's yes, I have to be careful with my inequalities. So if you want a circle like this, well, you can look at your donut as a superposition of 4 rectangles. And sorry, I have to make crossings here. And this is larger than, okay. FKG, which is larger than 2 to the minus 124. Okay, and by the way, okay, I'm doing everything with pictures. Well, somehow I think the general rule in geometry is don't trust too much the pictures. So yeah, like if you can find an analytic argument which tells you that this implies this, this is somehow better. And it's not very complicated to find one. Okay. Okay, so any idea for the third one? It's more complicated, but okay. So for the third one, the idea is to use two. So what's the connection between this event and this event? Well, the idea is that you're not connected to the box if you have a dual path that is circling around the origin. Okay, so if you're connected to the box, it means that you have no dual path circling around the origin. So the idea is to try to put down lots of donuts, lots of disjoint square donuts between the origin and the boundary of the box, and say that for all the donuts, well, each time you cross a donut, basically you're paying 1 minus 2 to the minus 124 to make sure that you have no contour like this. Okay, and all the donuts are independent. And how many donuts can you put? Well, something proportional to log n. Okay, just because, well, you have to grow them geometrically for them to be disjoint. Okay, so this is the idea when you get the exponent, and well, log 3 is actually the, log n over log 3 is actually the right thing, and this is what you have to pay for each donut. Okay, so this is reasonable. Let's see how it works in details now. So I will just define some sequence. So I will define n1 is equal to 1. I just want to define a sequence for which, well, a sequence of disjoint donuts, okay? So I just want to make sure that each time I take the next n, I get something which does not touch the other one. And when I'm doing this issue, when we're doing crossing, okay, we are allowed to touch the boundary of the rectangle. So this means that, well, we cannot make them touch each other, okay? They have to be really, it's not only the interiors that have to be disjoint, they have to be completely disjoint. Okay, so then the safe thing to do is to take nk plus 1 to be equal to nk, 3nk plus 1. And I think this is fine. We should do this. So this means that nk is equal to 3 to the k minus 1 over 2, okay, which is an integer. Okay, so okay, so now we are considering this thing. So you have 2ni here and 6ni here. Okay, and okay, so now let's define Kn to be the maximum of K, or the maximum of i's, if you want, such that ni is smaller, maybe 6ni, yes, 6ni looks good, is smaller than, say, maybe 6ni plus 1 will be better. Okay, I think this is fine. Okay. So now what's the idea? So I want these things to be living on the dual lattice. Okay, so what I mean here is that, I mean, I have to tell you, I mean, I'm giving you the shape, but to tell you exactly what this is, I have to tell you where I put it on the lattice. So I'm going to center it at 1/2, 1/2. Okay, which is something close to the center of the dual lattice, which has no center. Okay, it's kind of the origin of the dual lattice. Okay, so okay, let me call. How do you want me to call this? Okay, di. So what I'm saying is that the probability that 0 is not linked to the n, well, this is larger I want this is smaller, yes. This is smaller than the probability that for all I in 1 kn, there is no open dual path. Okay, dual contour in. Okay, where by this I mean no dual contours that circles the interior square. Okay, all my di stars, they are disjoint, so they depend on disjoint edges, so I have kn independent events. Each event has a probability which is smaller than 1 minus 2 to the minus 124. So this is smaller to 1 minus 2 to the minus 124 to the kn. Okay, and I think that kn is smaller than log n over log 3. No, kn is, yeah, I have to have a lower bound. So kn is larger than this, I think. So this allows you to conclude. Okay, you replace kn by this, and well, then you basically put this in the exponential, and you have to, and you put the log n down in order to have the n here. Okay, so this gets you, this is smaller than n to the power log, well, and let's see. Yes, okay. Log 1 minus 2 minus 124 times n over log 3 minus 2. So everything is okay so far? And just to tell you this, okay, you might know that this, okay, you might know that this is not optimal and this is not optimal, but actually you can improve it a little bit in the proof, but you would get really far from 5/48 in any case, so maybe it's not very important to try to make any improvement. The only idea is that you can make the bounds explicit if you want, and that's not very costly. This is the reason that I wrote it instead of writing there exists a constant. Okay. So far, what we have done is only using FKG in independence with a bit of geometry. Well, maybe you might think that you might do the same thing in order to prove that, to get a bound from this. Okay, you know how to cross a square. Maybe by drawing a bunch of squares and crossing them, you can get around. So let me show you why this is not the case. Okay, so just this. So you might say, okay, so I have 3n here. No, 3n here. Okay, so what I might do is just put n here and here and say, okay, I just have to. Yes. Sorry. Check what I want to do exactly. Okay. Okay, so if I draw two squares like this, I can say, okay, I can put a square in the middle. Okay, so here I have a 2n by 2n square. Here I can put n/2, n/2. Okay, and what I could say is, okay, with large probability, I cross this square. With large probability, I cross, well, with probability 1/2, I cross this square. With probability 1/2, I cross this square. And with probability 1/2, I will cross this square vertically, and all of this work. Well, the problem is that you could very well cross the square vertically without creating an horizontal crossing. Okay, and the idea is that it's not related to the fact that it's 3 by 2. If you have a rectangle which is longer than it's wider, okay, you will come into this problem. So even if you want just a bound for crossing a square which is n times 1 plus epsilon, okay, you will run into this problem. If you take two squares, and so you need to do something smart at some point. There is not only one solution, but okay, I think the one I'm going to present now is probably the simplest to explain and the easiest to draw. So this is what I'm going to do now. So what's the idea? So let me erase this. So I'm going to consider a square which is 2n by 2n, and inside I have a square which is n by n. Okay, and I will look at the following event. I will assume that I have a north to south path which is crossing this square. And I have a second path which can go, it can go everywhere, okay? Which is going from somewhere in this path to the left boundary here. Okay, so I will call this event AN. AN, so let me write the description. There is a north-south crossing path, gamma 1 in the small square and the crossing, okay. And an open path, gamma 2, from the left side of the big square. To gamma 1. Okay, is it clear what this event is? I'm just saying, you can find a bunch of open edges which are linking this side to this side. And then you can find a site on this path which is linked to this side using open edges. So the lemma I'm going to prove is that the probability of AN is larger than 1 over 8. Okay, and this is a difficult thing. Well, okay, one difficult thing is to figure out a good AN to play with. Then to prove this. But then by FKG, you can prove that, well, you can prove that the lemma implies that this is true. Okay, so any idea on how to show this from this? Just using FKG, okay? So the idea is that you need AN to be satisfied twice, in a sense, okay? and you need one more crossing of a square. Okay, so. Okay, so here you have two big squares, and here you have a small square, which is in the corner of the two big squares. Okay, so then maybe I can do something like this. Okay, I have some AN somewhere. So I am allowed basically to draw this picture, this sign once more, and one more crossing, and make sure that I have a crossing from left to right. So, any idea of what I should do?
You do the thing again on the other side from your root, and then get a crossing the small square.
Okay, so I guess just the symmetric of this one, right? Yes. Okay, and then I have to cross this from left to right. Okay, and I mean, you can check that it's not only the drawing, okay? Here I have gamma 2, gamma 1, gamma 1 prime, gamma 2 prime, and gamma 3. So I know that gamma 2 links me by definition to a vertex in gamma 1. I know that all the the gamma 1 crosses gamma 3, so I know that gamma 3 links one vertex of gamma 1 to one vertex of gamma 1 prime. I know that there is one vertex of gamma 1 prime which is linked to the other boundary, so this gives me my crossing. Okay, so this is what I tell you when I say don't believe the picture. I mean, it's really something that you can check. Okay, so okay, and here I'm using FKG and also symmetries of the lattice. Okay, the fact that here, yeah, I can place my small square everywhere and change the definition. Okay, this is just the same event, but where I've taken the mirror image. Okay, so now comes the hard part, which is to prove this. And for this, I will need to use some notion. So okay, so let's try to see what's the idea. So okay, so what I want to do is the following. I want to say, okay, I'm going to say, let's assume that I have a crossing here. Okay. Then what I can do is if I were good at drawing, what I could do is kind of symmetrize it, okay? Just abstractly, I'm just drawing this there, okay? And this defines me a zone here. Okay? And now what I can say is that I want to look at this zone, okay? Which is not a square. And to say, well, if I look at this zone, my probability of crossing it from left to right, well, it's larger than 1/2, because yeah, it's larger than 1/2 because it's larger than the probability of crossing the whole square. I want to square. Okay? And now if I'm crossing it, if I have a crossing, it might end up here or there. Okay? But everything is completely symmetric. So the probability, the probability of having a crossing, it's the union of two events. It's the probability of having a crossing ending up there, and the probability of having a crossing ending up there. These two events are not disjoint, but they have the same probability. Okay, so just by using the union bound, I get that this thing, okay, it has the probability of this thing. It has to be larger than 1/2 times 1/2. This 1/2 is for crossing the square. Okay, and crossing the square, the union of two things, it's the union of crossing the square and ending up here, or crossing the square and ending up there. And these are two events that have the same probability, so the probability of each of them has to be at least 1/2 of the probability of the full event. Okay, so far everything is good. The problem is that when I'm saying I have a crossing north to south here, okay, well, if I'm drawing the crossing, maybe I'm using information about what's in the whole square. So, in particular, I might reveal some information about what's here. Okay, and then this is not good because I might have revealed negative information, so the conditional probability might be actually smaller than 1/4. Okay, I mean, like, this is true for a fixed path, okay? But actually, what I'm doing is that I'm kind of selecting a crossing at random. And for a random path, I may be able to select this path, so this is actually not true. So what we have to make sure is that there is a way to select this path that does not reveal information on the right of the path, on the left of the path. Okay? So I think this will, okay, this might become clear but I just want to, now I'm going to go into some considerations about this, and I just want to justify that this hassle is necessary. Okay. Any questions about this? Okay, so now, if I have a path from north to south, okay, I'm going to define, so this is gamma. Okay, it's just a path from the top of the square to the bottom of the square. My square is n by n. This is a small square. Well, then okay, I want this to be self-avoiding. And then this divides the square into two regions, and I define the region which contain the right side, the left side, sorry, as gamma of gamma. Okay, so region delimited by gamma, top, bottom, and left side. Okay. So now I want to define another relation on the set of crossing paths. Okay? So on the set of self-avoiding crossing paths. So, and I want to say, I mean, this other relation, I want to say that one path is larger than another path if it's more to the right. Okay? So what's the right notion here? We want to say that gamma is larger than gamma prime if gamma of gamma is larger than gamma prime for the inclusion relation. Okay? So here is an example. Okay? Okay. And now what I want to do is to consider the rightmost crossing. Okay? And the idea is that if I consider the rightmost crossing, I won't need to know anything about the environment which is left to the crossing. Okay. So, but okay. So okay. So in order to make sure that there is a rightmost crossing, what's important is to say when you have two open paths, then there is an open path which is to the right of both. Okay. So let me draw this. Okay. So what most people will draw to try to convince you is, okay, here I have two paths. They are both open. Okay, I have two open paths. Then if I want an open path which is to the right of both, I just take this one. Okay, I just follow the red until the crossing. And okay, it's a nice picture, but it's a bit problematic for the following reason. So now if you have two paths that are like this, okay, then you can do this. Okay, so it still works. But you see that, I don't know, I mean, your paths are not graph of functions. So you cannot simply take the maximum of the two things. It's something that is a bit more complicated. And, well, then maybe it's good to make sure that, okay, that there is actually a way to describe this path. So let's try to do this now. So, so if gamma and gamma prime are two crossings, well, basically what you want to make sure is that there is an open path which includes, well, gamma of gamma and gamma of gamma prime. Okay? So, so now if you take the union of these two things, well, in this picture, it is exactly this. Maybe I've, okay. Okay, so there is no path that actually. So, okay, there is no. So this thing, okay, this. There is no path such that this is true. Okay, so you have to consider another set. And the idea is just to take such that. Okay, so it would have been cleaner. Okay, so I take this big gamma closed, so the complement is open. Okay, so if I take instead of taking the union, I take the intersection of the complement, then what I obtain is I have some set which is not connected, but which has two connected components. And I'm just selecting the connected component that includes the left boundary. Okay, so now the complement is something that delimits a path. Okay, and I know that this boundary of the component, well, it's included in the union of these three sides and the set of open edges. Okay, because basically the boundary which is not on the side, it's determined by these two other paths. So what I have is that, okay, basically the topological boundary of gamma is open. Okay. So gamma is open. Okay, so this gamma, I define it as just the maximum of these two paths. Okay, so okay, so let's say that I have a percolation configuration. So what I will do is end with north-south crossing. So just make sure that the set I'm going to consider is not empty. Now what I have is that I can define gamma max. Okay, I will just define gamma max. It's just, okay, so I'll just consider the intersection of gamma complement, where gamma north-south crossing. So I take all the crossing from north to south, okay, and I want to show that there is one which is right of all the others. So what I'm doing is, well, I'm taking the region to the left of the crossing each time. I'm making the intersection of all of them, okay? Okay, okay. Okay, so if you just take this intersection, okay, now instead of taking between two paths, you take the intersection of all the top to north to south crossings, okay, of the region left of north to south crossing, and then you just extract the connected component which is connected to the right side. And then you say, okay, this thing is delimited by a path. And then you can check that this path is actually a north to south crossing. Okay? And because of this definition, then all the other north to south crossings, they are left to this. Okay? Just because I've defined my order in this manner. Okay, so let's just take a small 5-minute break now, and afterwards I'll conclude this proof here. Okay, so just a small summary of what I just said. I don't know if the presentation was ideal, but the idea is that you can define an order on path by inclusions, okay, just by considering the region which is left of the path. Now, the idea is when you have two paths, you want to take the maximum of the two paths. Because this order was defined in terms of inclusion, maybe you can just take the maximum of the two sets. And a maximum of two sets for the inclusion, it's clearly the union that you have to take. Here's the problem that for paths, it does not exactly work like this. You have to take the union and then fill the holes. Okay, so this is the reason why I had to take the complement and then consider the connected component which touch the side. So maybe I don't know, I should have defined gamma as the other sides in order that I wouldn't have to. But the idea is quite simple. It's just fill the holes so that you make sure that what you obtain is the path. And then the important thing is what to make sure that what you obtain, okay. What we want to make sure is that our definition is such that if you take the max of two open paths, you get an open path. But this is true, because in the way you define things, basically, the edges, what you have is that the edges, the set of edges used by gamma. Okay, basically what you have is that okay, the set of edges that you're using for gamma. Second, it's included in the union of the set of edges used for gamma and gamma prime. Okay, all of these are open, so. Okay, and here I'm making this with all the set of north-south crossings, so basically I know that all the edges in all the gammas here are open, so basically when I'm taking the maximum, I know that the edges in the maximum are open. Okay. So, I mean, in the end, basically, gamma max appears in here, but this is what we need to prove. Okay, so meaning in this intersection, there is actually a smallest element. So. Okay. So let's go. So now we are going to do this, exactly this, but we are going to fix gamma. This is this is the important point. So now gamma is a fixed north-south path in the crossing in the small square. Okay, and if there is a north-south, an open north-south crossing, we call it gamma 1. Maybe call it max. Gamma 1 max. Okay, so gamma is a deterministic thing, like just a fixed variable. This is actually a random variable, which is a function of the percolation environment. Okay? So now what I want to make sure is that if I look at the event gamma 1 max is equal to gamma. Okay, this event. Okay, so this event, it's there exists a north-south crossing, and the rightmost of them is equal to gamma. Oh, we call gamma 1 max the rightmost one, sorry. Well, okay, so this thing is equal to all the edges of gamma are open, and if gamma prime larger than gamma, gamma prime different of gamma, then gamma prime is not open. Okay, in the sense that there is at least one closed edge in gamma prime. Okay, so if you look at the description of this event, what it's kind of clear is that it only uses the edges on gamma and the edges in this region, but it does not use the edges in this region. Okay? So in particular, whatever happens here, it's independent of this event. Okay, and now I'm going to use this picture, but now I have a gamma which is deterministic. Okay, so this is gamma, and this is, I don't know, gamma bar, which you obtain by symmetrizing. Okay, so now what I have is that the probability of, okay, so here is, okay, let me make it green. No, let me, okay, blue, I don't know. So, okay, so the probability that I have an open path from here to there, okay, and possibly going anywhere. Knowing that gamma 1 max is equal to gamma, well, okay, so what's important here is that now I assume that this path is not going in this square. Okay, just to make things independent. Okay, no, okay. Let me directly consider this thing with gamma bar here. Okay. So the probability that I have a crossing in this region, knowing that this is true, well, this is simply equal to the probability that I have a crossing in this region. Okay, I can just ignore the conditioning because these two events, they are independent. Okay, this event, it does not depend on the state of the edges there, okay, because I don't need to look at them to have the crossing. It does not depend on the state of the edges on gamma either, so I'm kind of safe. Okay, so now I have done the decoupling that I wanted. Okay. So this is now by union bound, this is larger than 1/2 of the probability of left-right crossing of this region. Okay. which is larger in itself than 1/2 of the probability of crossing the full square, which is larger than 1/4. Okay, so now we can conclude. So the probability of AN, it's larger than, well, it's equal, sorry, to the sum over gamma of probability that gamma 1 max equal gamma times the probability of AN knowing gamma 1 max equal gamma. Okay, this is larger than this, okay? This is actually strictly larger, okay, because for AN, you're kind of allowing to visit this region with this crossing. Yeah, actually for AN, you would even be allowed to do this, you know? But, okay. So, this is larger, okay, than, this thing is larger than this probability, and this probability is larger than 1/4. So this is larger than 1/4 times the sum over gamma of probabilities that gamma 1 max is equal to gamma. And this thing is exactly the probability that there is a north-south crossing, so this is 1/2. Okay, this is just the probability that gamma 1 max exists. Okay? So this is larger than 1/4. Okay, here there is a thing which is a bit improper, okay, if you want, that I have defined a random variable which is only defined of half the probability space if you want. But if you want to define gamma 1 max all the time, you can just say, okay, if there is a north-south crossing, then it's the rightmost path. If not, it's just, I don't know, the empty set or something like that. Okay, and here we are summing over all paths, and we leave the empty set away. So this is larger than, yes, 1/8. Okay, so is the argument clear? Okay, so this ends up with the proof part of today's, and maybe now I can kind of introduce, okay, try to introduce what we'll be doing tomorrow. So, okay, so what we've done is we've proved a lower bound on the crossing of some long rectangle, okay, which was something non-trivial. And what you can ask is, well, we know that this thing is bounded from above and below, so maybe when n goes to infinity, this should actually converge to something. Okay? So now the question should be, well, can you identify the limit of this? So yeah, can you identify the limit of this? Okay, and the answer to this question is somehow, okay, it's both yes and no. So the answer is yes, but not for the not for the percolation, edge percolation on the square lattice, but people have proved this for the percolation of the side percolation on the triangular lattice. But people believe that the result should be the same, so let me tell you what the result should be. So the result should be, okay, I don't really know what you should write there, but I can give you some kind of recipe to obtain this. So what's the recipe? Well, you kind of have to change the question to make it a more general question. So okay, so let me take a nice domain. Okay. And let me have 4 points on them. So this is what some people call a topological rectangle. Okay, so just something which is a rectangle, but the sides are curves instead of being straight lines. Okay, and what I want to know is what's the probability for a percolation process to join these two things. Okay, so what does that mean? What I'm going to, okay, so maybe this is, okay, orange is better than red, I guess. Okay, so the idea is I want to basically fix my quadrangle. Okay, so this will be something which is included in R2. And now I'm going to consider percolation on delta times ZD. Okay, so the mesh of my lattice, instead of being 1, it will be delta. Okay, and I want to know the probabilities that I have a crossing from there to there. So meaning just a path, okay, I mean like, maybe here, okay, I'm not using an edge, but just a fraction of an edge to go out. And the idea is that, well, if you send delta to 0, you should obtain maybe a limit for this probability of crossing. Okay, so what is this limit? Okay, so this limit is something that satisfies two things. Okay, so of crossing the topological rectangle. Okay. Maybe should. Okay, so I write should because it's not proof for the edge percolation on the square lattice. All what I'm going to say, it's rigorously proved, but only for the side percolation on the triangle lattice. So should satisfy. So first thing, and this is the important thing, is that if okay, so let me call okay. So this will be my topological rectangle. So omega is just the open set, which is the region which is delimited by my curve. And A, B, C, D are the 4 points on omega. So okay, so what I'm saying here is that if you have a conformal map that sends a rectangle on another rectangle, then the crossing probabilities are the same. What do I mean by conformal map? If you have D and D prime, two open sets of R2, a conformal map, well, it's just, well, I guess a C1 bijection from D to D prime, okay, such that, which locally conserves the angle. So what this means is that the derivative of phi is just always the composition of a rotation and a dilation. Okay, and now if you consider R2 as the complex plane, what it just means is that you have a function from a subset of C to a subset of C, which is bijective, and which is holomorphic. Because saying that the derivative is a rotation times a dilation is just saying that your function has a complex derivative. Okay, so a conformal map in R2 is just basically a conformal map. Okay, it's just a function from one open set, a bijective function from one open set of C to one open set of C, which is holomorphic. Okay, so I know holomorphic bijection, which is not defined necessarily on the complex plane, on the full complex plane. Okay, and what this says is that basically, yes, if I take this, if I just change the shape of it by applying an holomorphic function, I won't change the crossing probabilities. Okay, and I think the second thing is if I take an equilateral triangle, A, B, C, D, and this is one. What I have is that this is equal to CD, the length of CD. Okay, and the idea is that this determines fully the crossing probabilities, just because for any quadrangles, okay, there is always only one way. There exists one transformation that maps omega to this equilateral triangle, and that maps 3 points on the boundary to 3 points. So here I'm fixing A, B, and D. Okay, so if I want to know basically what's the crossing probability here, okay, I have a 2x3 rectangle. I just send it to the triangle, making sure that A, B, and D are the vertices. Then I wonder where C ends up, and this gives me the answer. Okay, so I think maybe the most important of the two things here is this thing, which is kind of magic. And basically, this is called Cardy's formula. And this was predicted by Cardy, I think, in the early 90s. This was proved by Smirnov in the early 2000s. So now it's also a Smirnov theorem. And okay, so what do you have to do to prove something like that? One very important step is to show that you have some kind of holomorphicity somewhere. Okay, that there is something in your system which is holomorphic. And if you remember your complex analysis lectures, one particularity of holomorphic functions is that if you take phi of z, this is the same thing as just taking the average of phi on the circle. Okay, well, this is the same thing as saying that the real and imaginary part of an holomorphic function, they are harmonic. Okay, so there is something similar that you can prove in the complex case, which is discrete holomorphicity, which is basically no, maybe I'm. Okay, I'm not not completely sure I'm saying the right things there. Okay, but okay, the idea is that there exists a discrete version of this, which is basically you place yourself on a graph, and you can ask yourself if a function is harmonic just by looking at the neighbors. Okay, and saying that the mean of the neighbors is exactly what you find in the center. So I don't think this is exactly sufficient. I think harmonicity is actually weaker than holomorphicity. Okay, but basically the important thing is that, so maybe the right thing to say is that if you take like really the contour integral here, you get 0. This is maybe the right signature of. Okay, so here I'm taking I was saying the average on the circle. Now you can take just the contour of integral of the circle, and you know that if phi is well defined, okay, this is equal to 0. Basically, there is an equivalent of this on the graph, okay, and well, not only if you have this basically and some tightness, you can get some statement like this in the limit. So this is okay. This is not the whole story, but this is kind of the starting point. What we are going to do next week is basically to show that if you have discrete holomorphicity of some sense, sometimes you can even use it directly to prove interesting things. And one particular case of this is the proof of the value of the exact value of the connective constant of the hexagonal lattice. So what we are going to do next Tuesday is exactly this, to prove that the connective constant of the hexagonal lattice is square root of 2 plus square root of 2, and basically use discrete complex analysis to do this. Questions? Okay, so see you next week.